Okay, I think that we are all. Okay, first of all, welcome to the first seminar of this new year. It's been a pleasure to introduce you the speaker of today, Teresa Bortolotti. She's a third year PhD student at the Polytechnic of Milan. And today's talk is entitled A Weighted Approach to Linear Regression with Partially Observed Function Data. So the stage is yours.
Thank you, Nico, for the nice introduction. Hello, everyone. So the title of today's talk contains a lot of keywords that I'm going to go through during the first part of today's talk. At first, I would like to talk to you a little about functional data and functional data analysis. First of all, my background is in statistics. So today's talk is a statistical talk. Okay. Then I will tell you a little bit about linear regression models in the functional data analysis context. I will tell you a few words on what partially observed functional data are and what are the criticalities that arise in the presence of partially observed functional data. And eventually, I will go through my, let's say, contribution to this topic, which is a weighted approach to solve linear models with partially observed functional data. So, sorry, lots of technical issues today. All right. Okay, so this is the outline, which is what I just mentioned. And let us first start with what are functional data. Functional data are entities that can be described through functions. They arise when there is a registration of a phenomenon that has a smooth variation and that varies over a certain period, which can be time, which can be space, or whatever. You might be interested not only in the point-wise analysis of these phenomenon and these variations, but also in the differential properties. And of course, the functional data set is just a collection of these functional data. What I'm showing down here is a notable example in the field of functional data analysis, is the Berkeley growth study. It collects the growth curves of males and females. And as you can see, each curve is identified by a set of longitudinal observations that reflect the smooth variation of height with respect to age of the people that we are recording. Some interesting features of these data are available only if you consider the derivatives of these curves and not only the zeros of the derivative. For example, the mid-spurt and the cubital growth spurt, so these peaks that you observe here. And in this case, for example, the grid with which the longitudinal observations are recorded are not the same for every curve. So for example, a classical multivariate approach, which would consider each of these age points as a different covariate, would fail in this context. Why? Because you had that for some girls or males, you have recorded their height at year 1 or year 1.5, etc. Another example of functional data is this one, where you have a numerical model that simulates the fluid flow in a subsurface in a reservoir. And the numerical model is the output of the numerical model is the field water production rate. These are the curve with respect to time of a quantity. This quantity is very relevant for assessing the performance of reservoirs. Here you are displaying the output of the model for different values of permeability. So to assess the performance of the reservoir, it may be interesting to do some inference for different values of permeabilities, also the ones that you are not observing. So it is interesting to do some statistical analysis on the outputs. And it is convenient to consider the outputs as functional data. This is an example that has a lot to do with the final application that we will see today. it has to do with a seismological data set concerning Italy. Whenever an earthquake occurs in Italy, there are some stations spread all over the Italian territory that register the arrival of a seismic wave. At the stations, the seismic wave is recorded by a collection of harmonic oscillators with a natural period of oscillation. Each of these oscillators record the maximum acceleration of the oscillator at the arrival of the seismic wave, so that eventually your seismic wave and in its intensity is quantified by what is called the acceleration response spectra, which again records the maximum acceleration for different periods. Since the spectra show a little bit of regularity over the longitudinal observation, it is convenient to consider them not in a multivariate setting, but in a functional setting. Now, what are the problems arising when you approach data of this kind with a multivariate, in a multivariate setting? Typically, what happens is that you find yourself in a large P, small n problem. When you have fewer observation with respect to the covariates that you are handling, you encounter, first of all, a huge problem of dimensionality, and then you are typically not able to derive any useful insight on your data. So in this context, classical approaches would basically synthesize your functional data, your longitudinal observations as very few indicators, and then perform the analysis on the indicators, of course, implying a huge loss of information. So instead, if you are interested in analyzing the functional data and generally in its entire characteristics, so its behavior, its first derivatives, second derivatives, and so on, you would preferably consider them as single elements, single points of a convenient space. And we will see that we consider functional data as atoms in functional spaces. So functional data analysis is the statistical setting that focuses on the analysis of data of this kind. It has been very active in the past 20 years. And basically was able to extend to the functional setting all the statistical methodologies that we have in a scalar and then multivariate setting. So of course, you have tools for exploratory data analysis, dimensionality reduction, statistical inference, regression, spatial statistics, and so on and so forth. All right, so as I was mentioning, the convenient embedding for analyzing data of this kind is to consider each functional datum as a point of an Hilbert space. Why? Because Hilbert spaces can be seen as the natural extension of Euclidean spaces, because through the notions of inner product and norm, you extend easily all the classical methodologies that you have in multivariate statistics. Examples of Hilbert spaces, you will see if you will ever study a little bit of statistics in this field, is that statisticians tend to produce methodologies in the general context of Hilbert spaces, but eventually they end up applying everything in the L2 space. So we typically work in the L2 space. The exception is that when you are dealing with functions that are constrained, so for example, density functions, in those cases, you may prefer working with bias space. All right. So just to have a little formal use, let H be a Hilbert space. The points in a Hilbert space are the functional data that are observed and defined on a compact domain. Here I will talk always about functional data with one-dimensional domain. Every methodology can be extended to two-dimensional, three-dimensional, n-dimensional domains. Then if omega is a space of events, F is a sigma algebra, and P is a probability measure, and omega Fp is a probability space, X is a functional random variable and is an element of this probability space. The functional datum is a realization of a functional random variable, and the functional data set is a collection of functional data. Okay, in this context, you can, of course, extend the notion of mean by defining a mean function, which is the solution to this problem here. So you consider the expected value of the difference of the mean from any other element of the Hilbert space. You take the square, and the solution is called the Frechet mean. In L2, which is where we typically work, it is possible to prove that the Frechet mean responds to the pointwise mean almost everywhere, which is quite convenient also because it gives you a very practical rule to estimate the mean function. You just take the pointwise empirical mean of the functions that you are observing. If x is a zero mean functional random variable in H, and it satisfies that condition of regularity, so its fourth power expected value of the norm is less than infinity, is finite. Well, the covariance operator takes this form here, which is maybe not so, it's an operator, of course. Its definition becomes very clear in L2, because in L2, the covariance operator is the kernel operator, so it is univocally identified by its kernel C, small c. Its definition, it operates through its kernel when it is applied to any function. And this, again, gives you a convenient rule to estimate it from data, because you can just estimate the covariance kernel by looking at the covariances at different time points. All right. All right. Of course, as I showed you at the beginning, we are not given directly with functions. We are given with longitudinal observations of these functions. So when we deal with functional data and we want to approach the statistical problem from a functional data analysis perspective, a first step that we have to do is convert the raw data into actual functions. So whenever we observe longitudinal observations that, again, are not necessarily all observed on the same grid, what we want to do is understand what the underlying function is. We assume that the longitudinal observations are noisy observation of an underlying function. And the steps to identify this function x underlying the data is, first of all, you need to choose a target functional form, and then you need to estimate the optimal function within the space of the target function. Okay. So, first of all, to choose the optimal functional form, you need to understand what are the features of the data that you're interested in. If you're interested in second order derivatives, of course, you need to define your functions in a way that the second order derivatives are well defined. Typically, what we do, again, we work in the L2 space, and we operate a basis expansion of the target function x through a system of basis functions. A system of basis functions is a collection of known functions that are linearly independent, and you assume that your x can be arbitrarily well approximated by the basis functions and by linear combination of the basis functions. So basically, your x can be written in this way, and it is identified univocally by a vector, k vector of coefficients. So if you need to estimate x, you need to retrieve the best coefficient possible. Of course, here, the larger k, the assumption here is that the larger k, the better you are approximating your x. Why does this make sense? Because in L2 is a separable Hilbert space, so you know that there always exists an orthonormal system of functions. So, for example, if these were the eigenfunctions of the Hilbert space of L2, then you would know that if k is equals infinity, you are able to completely reconstruct your x. This is the theory underlying this entire methodology. Okay, so once you have selected your system of bases, how do you find the vector of C? Well, you basically you look at the problem as a regression problem, where you assume that your longitudinal observations are the noisy realizations of the function that have an error. Why am I omitting here the pedix I? Because this procedure is applied function by function. So this entire procedure is typically called the smoothing. The smoothing is performed. The smoothing that you do on a function is not affected by the smoothing that you're doing on the other functions. Okay. All right. So again, yeah, you have a regression problem, and the typical way that we adopt to solve this regression problem is through the least squares and through the introduction of a penalization that, let's say, reflects the desired properties of regularity of the function that you are looking for. So if you are looking for a smooth function, you may want to introduce a penalization of it on its second order derivative, so that the selected function eventually is as regular as the weight that you are giving to this part here. This part here is the least squares. Lambda is called smoothing parameter. The larger lambda, the smoother the resulting function. The smaller lambda, the rougher the resulting function is. Lambda, okay, we set lambda through generalized cross validation. And why is this a popular solution? Because there is a result from Debord in 2002, which tells you that the optimal system of bases that solves this minimization problem is a specific system of bases that is called B-spline, and specifically cubic B-spline. So when you select this criterion from going from raw observations to smooth functional data, when you select this criterion, you already know what is the basis expansion that you are looking for, because the board tells you that the optimal one is the cubic B-spline. I didn't tell you about B-splines, but it's a system of bases that is super flexible and allows you to either retrieve very rough functions or very smooth functions. Yeah. Yes. Okay. So now that we have our functional data, what we want to do is do linear regression. In Hilbert spaces, you can have, when you consider Hilbert spaces, you can either have functional or multivariate responses or functional or multivariate covariates. The combination of these two gives rise to 4 possible models. I am going to talk to you about system D here, which has functional covariates and functional responses. Note that this model here can actually take 2 forms. One is similar, it's called concurrent functional model, and basically tells you are assuming that the impact that the health covariate has on the response at t goes through solely the value that that covariate has at t. There is a more complicated and more general model, which is called functional function, where the impact of the health covariate on the response at t goes through the entire range of values that the covariate takes, let's say, over the entire domain, or at least a portion of the domain. And the influence of the covariate is mapped through the coefficient, which is a function of 2 variables. Okay, here there is a linear product. All right, so again, we are going to see the simplest case, which is the concurrent model. This is our model. We have a functional response, functional covariate, and we want to estimate functional coefficients. In matrix notation, this can be equivalently be expressed like this. And Z is the generalization of the design matrix of simple linear regression models, which is let's say it's a function. So the design matrix changes its value for each value of our independent, let's say, variable. Okay, in order to fit this model, we typically introduce a roughness penalty on the coefficients that we are looking for. Again, when you do functional data analysis, what you typically want to do is to regularize as much as possible. You are assuming that the phenomenon that you are recording has regularity properties. So when you can, you always regularize. And the way you can add any kind of penalty, again, what we typically do is that this L here, so the penalty operator, is just considering the second derivative to penalize the roughness of the estimated coefficients. This is the functional that you want to minimize. This, again, is the classical least squares. The only difference is that you are integrating the functional errors at each t. Okay. Now, this is an infinite dimensional problem. Beta is an infinite dimensional quantity. So in order to solve this problem, you need to reduce the dimensionality. What you do again is that you go through basic expansion. So you assume that the coefficients that you are looking for are defined on a space of basis functions theta. And what you really estimate is the vector of coefficients with respect to this basis function. This is a super general notation. You need to estimate K. Sorry, what is the P typically? Let me see. Q, sorry, you need to estimate Q parameters, okay? By using this super general notation, you are assuming that each functional parameter is defined on a different set of bases. Because a priori, you may have some information on the characteristics of regularity or of density in some different portions of the domain. R is the penalization, again, generalized, considering the fact that each coefficient may have a different basis. Okay, once you do this basis expansion, the model that we saw before can be expressed in this way, where your only unknown quantities are contained in this vector B. And then by using basic properties of the connected product and linear algebra, you find out that B can be found solving this equation. So you invert this quantity, you evaluate this quantity, and you find B. This is the basic, if you have some reminiscences from, I don't know, statistics 101, okay, this is the solution of the coefficients for the linear regression model, just extended to the functional setting. All right. Am I going fast or slow? Okay. All right. Now, let me add a little piece of notion that leads us toward the core of the talks of today. What are partially observed functional data? Well, it may happen, and it typically happens, that your functional data are not completely observed over the domain of definition. So formally, the realizations xi are observed only in a subinterval OI of 0,1 without loss of generality. So that your functional realization can be written in this way. There are possible regimes. Here I reported only two. The blanket regime is the regime where the missingness, the pattern of missing can happen anywhere and are not the same for the functional realizations. In this setting, it is typically easy to retrieve the estimators for the mean function and the covariance operator because you still have enough observation at each point and at each combination of points for the covariance kernel. In the bounded regime, you are assuming that each functional datum is observed only on a length delta of the domain, but this delta can happen anywhere. In this case, it is still easy to estimate the mean function. It's not easy to estimate the covariance kernel because you never have observations at of the same function at different points of the domain. So when you want to estimate the covariance kernel anywhere in the 0, 1, 0, 1 domain, there are some spots that are missing. So these are issues that are being tackled in these years. Current research is focused on tackling these kind of issues, for example. So, as you already understood, when you have partially observed functional data, you have no straightforward estimators of the mean and covariance operators, and also you cannot directly apply the techniques for functional data as they are. You need to find ways to go around the issues. Okay, so current research has focused on the estimation of the mean and covariance operator. Here I put just some references, if you're interested. I'm not sure. And then on the identification of functional principal component analysis, which is the extension in the functional world of the principal component analysis. And then another field of research focused on curve reconstruction. So the imputation of the missing trajectories of the curves where they are missing. The main references are those two. For example, the reconstruction method of Krauss relies on the estimation of the covariance operator on the observed part, restricted on the observed parts of the curves, the covariance operator from the observed part of the curve to the missing part of the curve, and then operates the reconstruction of the missing trajectories through a mapping of the observed part through the combination of these, the composition of these two operators into the missing part. Okay. If you are familiar with the technique, this is very similar to kriging. Kriging is a technique for spatial analysis, spatial data analysis, when you want to do predictions of values in points in space where you didn't observe the value. You can think of a, let's say, a functional reconstruction counterpart of kriging. All right, so these are examples of techniques that are being developed for partially observed functional data. This leads us to the heart of today's talk, which is a method that myself and some co-authors developed for doing a linear regression model, a concurrent model with partially observed functional data. What is the motivation? We wanted to extend to the functional setting a ground motion model that is available for the Italian territory. It is developed by the Italian Institute of Geophysics and Volcanology, which is based in Milan, at least the Milan section. So it is a model that, given an earthquake scenario, aims to predict the acceleration response spectrum in different parts of Italy and for different values of the periods. So for the entire spectrum. Why so? Because it is, the quantity is very important for understanding the responses of buildings to the arrival of seismic waves. The current scalar model builds the model period by period without considering the correlation between periods. Of course, to address the correlation, you would build a multivariate model, but this is one of the cases where you have a big P small n situation. So a functional model is better fitting for in this context. What is the problem is that these intensity measures are only partially observed sometimes. So for example, here I am displaying the fraction of observed curves per period. As you can see, all curves are observed for small periods. Here the periods are represented in logarithmic scale, but for the long periods, a lot of information is missing. So in front of this challenge, we had three alternatives. We either cut the analysis only in the, this is a 0.0011 domain, But this is infeasible, mainly because the seismologists are interested also in estimates at long periods. Or we considered only the curves that are completely observed over the entire domain. But this is also not really acceptable because you throw away a lot of information. So we had to opt for a solution that is somewhere in between, and we came up with what we called weighted functional data analysis. The idea here is that you use one of the methods for functional reconstruction so that you retrieve the entire information over the whole domain. And then you introduce a system of weights that is observation specific and that point by point is telling you how reliable that longitudinal observation is for your analysis. So the idea is that the system of weight for the observation I takes value 1 where the observation is available and decreases to 0 the more the reconstruction becomes uncertain. And in order to introduce this system of weights in our analysis, we had to redefine the optimization criteria for the concurrent linear regression. And this is what we did. Okay, so this is again the concurrent linear regression that I just showed you. The only thing, the only thing that changes with respect to the previous case is that now we add here in the least square part, the weight. Again, in order to fit this model, we make the assumption that the coefficients live in a finite dimensional space so that they can be uniquely identified by vector D. And we redefine the closed form solution for B by accounting for the weights that we introduce. This is a matrix that depends on S and that contains the weights observation for observation. The weight matrix appears here and here. Again, this looks very, very similar to the classical linear regression. All right, now this methodology is self-standing. We decided to add, prior to doing the regression, we decided to do the smoothing of our curves because they have some level of roughness that is basically noise and not really explicative of the behavior of the response spectrum at each period. So we came up with a weighted counterpart of the smoothing as well, where the weights appear here. Okay, so the weights for regression and for smoothing could in principle be different. We decided to set them as equal and see what happened to the regression performance. Now, how did we pick the weights? First of all, we came up with a very naive solution. Since our curves are right-censored, we defined the first system of weights as logistic curves. They are not really logistic. They are the composition of a constant function at value 1. And then they logistically decrease the further you get from the last observed point. This definition depends on two parameters, the scale parameter and the location parameter. The scale, we decided to fix it at the mean point of the missing domain for the ith observation, partially observed observation, while for the scale, we decided to make it depend on the variability of the curve at the last observed point. And then the parameter I is, we consider it as an hyperparameter that we can tune via cross-validation. Okay. This is naive. It works only for our problem at hand and for, in general, problems with curves that are right-censored. If you wanted to have a system of weights that works in a more general setting where the pattern of missingness is where the missings can occur anywhere, you may rely on these reconstruction-driven weights that, again, so you assume that yi is observed only on its domain, observed domain OI and missing on MI. The weight takes value 1 in the observed domain and takes this value in the missing domain. This one here is the diagonal of the kernel of the reconstruction error. This one is the diagonal of the kernel of the original covariance operator. This is the covariance operator of the reconstruction error, okay? This quantity then quantifies the reduction in uncertainty that you get through reconstruction. So if the reduction is very high, then this value is high and is close to 1, which is the weight that you give to the observed curves. Okay? This is intended to be a more general and more solid way of defining your weights. Okay, then we wanted to see how our method performed on a simulation study. So we generated some coefficients, we generated a functional covariate and a scalar covariate in order to make the simulation as general as possible. We generated our responses, and we generate randomly a pattern of missingness for some of the responses that we had generated through the simulation study. This is an example of partially observed curve, where the empty dots are the observed curve, observed points, and the full dots are the reconstructed points through the method of Krauss, the one that I mentioned before. These are possible weights for this curve. So for example, this weight here corresponds to the situation in which you neglect all the reconstructed parts of the curve, so you restrict the analysis only on the observed part. I didn't represent the case in which the weight is everywhere 1. And these triangular dot points here are the reconstruction-driven weights, so the more general one, and all the other curves are the curves of the logistic weights for different values of A. Just to show you that the logistic way of defining your weights generally gives you a little flexibility. So it is not so bad, at least for our purposes. Okay, with the simulation study, we wanted to assess the robustness of the coefficients estimates of the regression with respect to the reconstruction method. And the other one is that we wanted to assess the accuracy of the coefficient estimates for different definitions of the weight. So here, for example, this is a result that you get on the accuracy of the coefficients, the coefficient estimates, with respect to different methods of reconstruction. What we see here is that so these are the box plots that you get over 100 repetitions of our simulations of the error in the estimates when you do not use a weighted analysis for different values of reconstruction methods. Here are the errors that you get when you use a weighted analysis. What happens is that when you include weights in your criteria, the method that you use for reconstruction typically matter less. You generally are able to reduce the estimation error that you make. And this reduction is very significant regardless of the reconstruction that you're using. So basically, the take-home message here is that if you have partially observed data, you can decide to reconstruct your data with whichever reconstruction method that generally works, and then include the weights, because eventually the difference will not be so much. Okay. Here we are assessing the estimate of the accuracy of the estimates of the coefficients for different definition of the system of weights. These two extreme cases, the first one is the unweighted analysis, so the state of the art, let's say. This one is the results that you are getting if you neglect completely the reconstructed parts of the curve, so if you restrict the analysis only on the observed part. And these are all the results that you get when you add a possible system of weights. Now, our question, so this is basically telling us that at least in accurately estimate your regression coefficients using the weights makes sense and leads you to more accurate estimates. Now our question was, how can we identify a criterion for identifying the best possible system of weights? We did another simulation experiment, and we found out that using a cross-validation by considering the error that you make on the observed part of the curve, the y, so the responses in the entire regression, after the entire regression routine. Well, if you look at the cross-validation error, you can identify a minimum and you can select the best system of weights. So this basically tells you that it is a methodology that you can use in practice, because in the practice, you do not have access to these quantities, of course, because you don't know the true beta. Okay. Okay, now going to the application, this is the parametric form of the ground motion model that is currently used for Italy, and then we wanted to extend to the functional setting. So these are the coefficients of the regression, and these are the covariates. So for example, these ones are categorical covariates indicating the style of faulting, whether it is slip or fast faulting or something like that. These are the covariates indicating the magnitude of the earthquake. These are the covariates that depend on the distance of the station from the epicenter. R is indicating this distance. And yeah, we extended this to the functional setting. So you have to imagine that all these quantities now depend on the period and are functions of the period. Critical steps here are the calibration of the ridge penalization parameters. I didn't really mention anything on this, but if you saw in the penalization term in the regression, each coefficient had its own smoothing parameter. So if you are fitting a model with 9 coefficients, you will need to tune 9 parameters. We decided to improve the parameter selection process by using a generative algorithm from that we got the inspiration from this paper from Fabio Centofanti, and it is a method for parameter selection that is typically used in deep learning, and it allows us to reduce the time to converge to a stable solution of this set of parameters. Okay, then we had to choose the weights, the system of weights, then we had to choose the reconstruction method. Again, we already saw that using one or the other reconstruction method, it's not so relevant once you insert the system of weights, so this step is not so mandatory. You could also use one reconstruction method of your choice. And then we obtain estimates of the functional regression coefficients. And this is an example of the estimates that we get. I just wanted to plot them to show you the effect of the inclusion of the weights in the resulting estimates. What you typically observe is that over the entire domain of definition of our regression coefficients, the functional estimate, which is represented by this black line here, adheres very well to the point estimates obtained by the scalar model. The differences appear in the last part of the domain, which is where the missing values are happening and where the system of weights is coming into action. And the thing that the system of weights is doing is that it is regularizing the resulting estimate in the last part of the domain, so at long periods, which is also where we have the least observations. And this is happening also for this other coefficient, but it's actually happening for all coefficients. I just didn't have space to show you all. What are these boxes here? It is the functional box plot, which is the functional generalization of the box plot that is using statistics. It is the property that it is indicating the most central area where all the estimates of the functional coefficients from a bootstrap methodology applied to our ref model lie, okay? Basically, this box here is telling us where most likely the true regression coefficient is going to be. It is a measure of uncertainty quantification. All right. Okay, the conclusion of this talk is that whenever you do an actual analysis on functional data, what typically happens is that since the methods are young, you usually need to extend the current methods to your need, because not all methodologies are already there for all possible needs. In the specific case of the method that we proposed, it proves effective in reducing the impact of the reconstruction method on partially observed functional data when you want to do linear regression with the partially observed functional data. And it improves the stability of the regression coefficient estimates, which is also quite good. And the nice thing and take-home message is that when you have partially observed functional data, the optimal solution for performing your analysis is found in the middle between restricting the analysis only on the common observed part of the curves, or reconstructing the curves and forget about the reconstruction. And this is something that completely aligns with the result of a completely independent study, that is that of Stepanucci, Sangalli, and Brutti. And actually, for example, now I am doing another study on partially observed functional data, and in a completely different context, again, finding the solution in the middle between considering and not considering the curve in the missing part is always the best choice. So these are indications that what we are doing is actually, it does make sense. Okay, so the code is here. The references of all that I told you today are here, and thank you.
Thank you. Are there any questions from the audience or from online?
Probably I can start. So thanks a lot for the very interesting talk. Okay. So can you go back to the assumption that you make at the beginning on the linear representation for your functional data, like where you have essentially this sum over the CK and the VK.
Yes.
Something like that. Yeah. So in this
so
case,
in the smoothing, you mean?
Yeah, exactly. Yes,
Here.
yeah, exactly. So in this case, if I understood correctly, the CK are essentially the coefficients and the VK are the basis.
Yes.
Okay. So what's because like usually in, let's say, in our context, model order reduction, we usually do, let's say, sometimes the other way around. So like we let vary the coefficients with respect to the parameter, and then we keep the basis fixed.
Yes.
So let's say why you need, let's say, so which are for you the, let's say, the kind of consequences of considering, or could it be interesting to have a fixed basis and having varying coefficients? Or so probably they're the points that you're actually interested in, the coefficients. So this is what you want.
I think that we do the same thing. So I am assuming that the phi here, which are the bases, are known and fixed.
The phi, okay, but it depends on time.
Oh, okay, no, yeah, they are functions.
Yeah, exactly. So for us usually we have we can build let's say a basis which is fixed once and for all for all time. Yeah, for all time. Yeah.
And then
I'm not saying that it's the best thing. Of course, it's not.
I'm just trying to understand.
Of course, it's not in this case. That's actually my question.
So what you do, but you are not tackling a statistical problem, are you?
No, sure, no. Like we have like evolution, but still we have evolution problem. So in fact, you should not do that for time-dependent problem. So this is actually time, no?
So what you do is that you retrieve some functions.
Yeah.
With respect to some fixed basis indicated by scalar quantities.
Exactly. Yeah. Then we let derivative exist. So if you have, I don't know, just some.
In our case, we do this because in statistics, what you do is that you retrieve they see from the data.
Yeah.
If your unknown is an infinite dimensional quantity, you cannot do it because you don't have enough information for that. This is why we do this basis expansion, which is basically a dimensionality reduction of your problem that you can then solve by looking at a finite number of values.
So in this fee then are built like the spline that you were saying before?
Yes, these are.
So that's what you know, that's your...
In a naive case, the fee could be, the fees from 1 to infinity could be the eigenfunction.
Yeah.
But it's fixed, right?
They are fixed.
Yeah, it's a functional approximation
Yeah.
at the end of the day.
Yeah.
It's just that they have the coefficients like the determining those kind of data outcomes. And absolutely we have truncation error. But in this case, the absolute over there is a random variable. That's correct.
See? You mean? Sorry, what is a random variable?
Either absolute, I don't know what it is called.
The C's are random variables, yes.
So that's a random.
Yeah. Again, the rationale behind this approach is that X is a function belonging to a separable hearable space.
Yeah.
So you know that there exists an orthonormal basis. And that if you take the infinite linear combinations of these infinite orthogonal bases, then you retrieve X exactly. So if K is super large, then you are assuming that you are very, very close to the true X.
Yeah, probably the difference is just
I actually think that we actually do the same thing, not with time, but for space. We do the
Yeah,
exact
it's
same
functional
thing.
approximation.
Like if that T is for us what we do with space is what we do with POD, for example.
Yeah, the
We
parameter is the
assume a
random
discretization.
parameter in the gravity space, for example.
Yes.
And so C is dependent on the omega
Yes,
belonging to,
exactly.
and about that,
It's the same, it's just different P. That's it. That's it. If you do anything, you do this for some other method. It's functional approximation. Most cases.
about that, I have another recipe, maybe some slides next. I don't remember when you talk about the theta.
The
The theta
oh yeah,
matrix.
here.
Okay. Here, because here your beta is like the basis that we were talking about. Right?
The theta.
The beta here.
The beta is the unknown regression coefficient.
Okay, it is a known.
So you assume that you have some response that this is a regression problem.
Yeah.
Okay, you have some response which happens to be a function,
Yeah.
but it's still a response in a regression problem. You have some covariates, and you have the coefficients that map the covariates into the response. So your goal is to estimate the beta. Since this is an infinite dimensional quantity, and again, we are statisticians, so we have only observations, we do the basis expansion of the beta.
And are the theta somehow connected to the covariate Z?
No, they are actually assumed to be completely independent.
And how do you take theta?
It can be any orthonormal function or the B-spline basis or whatever prior assumption you have on the coefficients of your regression model. If you want the resulting estimate, for example, if you have no prior assumption on the smoothness of the coefficients that you want to estimate, you may take this basis. Each object here is a system of bases. Okay, this is what I mentioned before. Okay. If you have no prior assumption, for example, on the smoothness of beta 1, this could be a B-spline, cubic B-spline basis, which is one of the most flexible system of bases that we have. And you may play with the penalization here and see what happens if you give very little weight to the penalization for that object or a very high weight for the penalization. Sorry.
Yeah, I was also wondering if having some selected choice of theta and Z could lead to a more computable thing in the case of the integral that you have there. I don't know how difficult it is to compute that integral.
Sorry, which?
The integral in the bottom of the page here. You have some.
It's actually easy because the result of this operation is another matrix that depends on T. So you basically, this is applied, I didn't mention it, but this is applied component-wise of the matrix.
Okay.
So you are basically computing a lot of different integrals of a function. So they are not actually complicated, but there are other approaches to functional regression where you basically consider as a one unique object both the covariate and the coefficient. But they require a completely different approach. So this is the reason why I didn't mention them to you.
Yes, good question. So that is given as an input, right?
Yes.
So it's you have a response and y is the response.
Yes.
Okay. Okay. So this is there's one thing that I think is very similar to this in what is more my field. That is dynamical variation networks. So this theta represents the evolution of those weights in that network, and we have a very similar formula for what we do there. And my question was related to the variation part. There's an algorithm that also works for functional data like regression process. But I don't know if there is an extension of regression process also for time, because what you're basically doing is you have some input and some points, all right? That could be seen as realization of those regression process, and then you close and open the gap depending on if you're observing or not observing. It's basically what you do with the weighting. But I don't know if you have looked at also these type of algorithms when how they perform in this kind of extrapolation is what you do at the end of the day regime. So if you have worked with those as well, and can you compare?
I haven't. I heard of these methodologies. I didn't really look at them. Why? Because our final goal, let's say the origin of this entire analysis was the formulation of the ground motion model. In this field, interpretability is the crucial aspect that you want to have at the end of the day. And I'm afraid that with those kind of models, you completely lose interpretability. Am I right?
Regression processes.
By modeling.
No, variation models, yeah.
Yes.
No, that was just for connecting the formula.
Okay.
We're talking about regression processes.
Okay.
So if you, sorry, two separate questions. One was the formula that is related to what I do, and it was interesting to me, and the other one is the regression process that usually work in functional spaces. So it was just a question if you compare these models and
you mean if I try to model the response as a Gaussian process?
Yeah, something like that.
Where an additional process is put on top of it to make the observation observed or not observed.
Yes, exactly. Because I think it's the same problem, right?
I think it is the same problem eventually. And I think it could be done because then you basically, I think that what you would gain is a completely new way of defining the weights and parameterizing the weight system.
Yeah, exactly.
I didn't do it, but I think it could be done.
I mean, over there, what you do is instead of adding the weight, you have a hyperparameter, and you take the maximum local likelihood and then you minimize your maximum load. I don't remember. That's pretty much. Instead of weights, you have a hyperparameter.
Yeah. I see.
That's it. And whatever is the best result, go back to the circle. So so you mentioned the comment that your data is noisy, which I understand. Then you have to denoise it before giving it some parameter. Now, my understanding is that during this process of some tuning, some coefficients or the weights or whatever it is, we're dealing with expectations, moments, and these moments are usually very smooth, but they don't appear very noisy. So you probably take the second moment or the third moment, they're going to be very smooth. So why do you have to be noisy?
Well, first of all, it is, you mean when you go from raw data to smooth functions? Is this your point? Well, first of all,
in that process, you're actually, it's some kind of a regression problem. So you have some parameters to determine, and those things work very well when you have smooth data and not noisy data, not noisy data, right? So that's why you denoise it, correct? So that's the question.
Let's say the smoothing procedure can be seen for sure as a way of denoising, but also as a dimensionality reduction technique in a smooth way. So instead of considering, for example, a simple interpolation of your discrete observations, for example, a simple interpolation of your discrete observation would completely hinder the possibility of doing analysis on the first order derivatives or the second order derivatives. The second, no, because they are not defined. So this is one reason why you go for another approach.
How are you doing it? How do you do it?
Through the basis expansion.
With the basis expansion.
Yes.
Then you have an additional term, which is a random variable.
Yes, but you estimate it. So you basically consider the problem in cascade.
Okay.
So first you retrieve your functional data through this process, through this procedure, and then you do whichever analysis you want to do. The procedures are different. Why? Because in the first part, so when you have your longitudinal observations and you want to retrieve the function, you do some kind of regression analysis on the longitudinal observations. Once you have done this procedure for your entire functional data set, then you do the proper statistical analysis on your end observations.
Basically, you're putting y equal to y equal to ck plus the sum of y equal to ck plus. That's what you're putting, right? You're finding c in here.
Here, yes.
Yes, you're finding c.
I'm finding C1, CK.
So the data is noisy, and you have an additional term which is epsilon, which is the location error.
Yes.
And that's, if your data is noisy, then that term is also a random variable.
Yes.
So if that term is a random variable,
Yes.
then I will either have to take an expectation or I take one representative value or something like that. Maybe maximize or minimize the worst case scenario or something
Yes.
like that. You see?
Yes.
If you have to do that, so how do you
But it's wait. The error that you have here is zero mean in this direction. It's assumed to be zero mean in this direction. It may not be zero mean in this direction.
Okay, but the epsilon is that the question is on the epsilon. Y is equal to ck plus 5k plus the additional term, which is the random variable. That's the noise. You need one value for that. Either you can do a maximum value, you can take a minimum value, you can take an expectation. Understand?
No,
I'm
sorry.
So
I'm not.
Write down
Yeah.
y equal to the sum of.
So y equals the sum
of ck, the sum of ck 5 plus the additional term. Now in this equation, phi is known, y is known, and y is a random variable. So see, phi is known.
Yes.
Y is known. Is your observation. That's your observation, which is your random variable. That's a random variable. Yeah, that's a random variable. So if I have to subtract this term, the epsilon is a random variable.
Yes.
That's a random variable.
Yes.
Right. So it's not one value. It's actually multiple values dependent on t.
Yes.
See, so So when I have to do this optimization procedure, when I have to do this optimization procedure of finding the best seed, I have to fix some epsilon. Either I take a mean or I take a max or something,
Okay.
right? How do you do it? What are you doing? Is the question.
I am basically minimizing the squared errors.
The square. Okay.
The errors are entering my minimization criteria for finding the C.
Okay.
As in regression problems.
Okay. Okay. So you take the squares and you take the square root and take the sum of it.
Yes.
The sum of it becomes
This forces your reconstruction, let's say, to produce errors that are very close to zero.
Yeah.
If you didn't include the penalization term, you could even interpolate eventually and get here zero for every observation point.
Yeah, I mean,
Since you include the penalization, I don't think you're doing
you're trying to minimize epsilon because you will have to fix. You have to, the A is the n is fixed, so you have to minimize epsilon.
Yes.
Yeah. So that's good. So okay. So then you have this leave one off strategy that you have in your experiments, in your computational experiments, leave one off strategy for cross validation.
But it is a different problem at that point.
Okay.
Because eventually in my experiments, I focus on the regression problem. Okay, so the cross-validation strategy is concerned with the reconstruction of the functional responses as originated by a linear regression model. So it's a different problem.
So when you're like, again in this setting, I mean, I will remove one data point and then I will optimize C and I will continue doing this, right? This is what exactly you're doing it, right?
This is okay. This is a procedure to find the optimal C.
Yeah.
It is not what I was doing in the simulation study that I showed you. Okay.
So sorry, I missed it.
When I arrived, so this was part of an introduction to the functional data analysis framework generally, no?
Okay.
Then I mentioned to you a new way of performing a linear regression model in the functional setting. Okay. And eventually what I showed you is the performance of this new way of doing it on stimulated data through a cross-validation, but done for selecting another thing, let's say, okay, another parameter that entered the model. And this parameter was the parameter defining the weight.
Can I see? Okay, the parameter defining the weight of it. Okay, but then it's also a regression scheme.
It's a regression scheme, yes.
And the new thing you mentioned is that if you least square minimization problem, you have a additional weight. That's the new thing.
Yes.
That's the new thing.
Yes.
So if the least square, what exactly are you doing? Okay,
I'm doing this. I'm changing the way in which you identify your regression coefficients, your functional regression coefficients, by including the system of weights here in the least square part of the entire minimization problem.
Based on the results. I have a question. Very, very fast.
Yes.
Next, I have to wait.
So I have another appointment.
Ciao. Okay, so my question here, actually curiosity. So for different betas, so for different coefficients in expansion, you get that different, first of all, you get different uncertainties for the weighting. Meaning there's more variability in the first coefficient than the other ones, which makes sense because it's, I think,
It's the intercept.
Yeah.
Yes.
But then what to me is not it's strange is that also there's not clear pattern, right? There's not a, for example, A equal to 15, which is the one that by cross validation should be the best.
Yes.
Is actually the best
For every coefficient.
Yes. So it was if you have an explanation.
I don't. Here, the reason why you have for each regression coefficient a different scale of the error is that the coefficients themselves have slightly different scale. The pattern may be due to scale, I'm not sure. The idea here was not really to identify a system of ways that could optimize at most for all coefficients jointly. You would want eventually to find the best system of weights that could decrease the prediction error on the Ys and the response. This is why we did the cross-validation methodology for selecting the best system of the weights. What we wanted to see with this experiment is, okay, the optimal solution must be around here, and for sure is not here or here, which are the two extreme solutions. So I think that what I want to stress also is that we for sure didn't identify the best way to select or to include the weights in the model. Our take-home message is you should include weights. There is still work to find the proper and more general definition of these weights.
Yeah, that was also clear by the graph that slide before about the weights that you should include.
You mean through the reconstruction? Yeah, here you mean. Yeah, here I think the nice thing that you find here is that when you include the weights, then the reconstruction is not so relevant. For example, to me, understanding the reconstruction by studying the paper was not trivial back in the days. So if one could tell me, okay, use whichever is implemented and go on, I would have done it. So no, just to say that they are actually effective in reducing the variability of estimates, which is nice.
Yeah, that's really impressive.
I would encourage further research on the definition of weights that are very general and very effective. This for sure is not exhaustive at all.
So I think that we can thank our speaker again.
And we talk about this session.